So good morning, everyone. My name is Themis Prodromakis. I'm the General Chair of MEMRISYS 2025. It's really an honor and a pleasure to welcome you all to this year's MEMRISYS and to the beautiful city of Edinburgh. And it's really a great honor and privilege to introduce our first plenary speaker, who is Professor Leon Chua. I think Professor Chua really needs no introduction. I felt really hard of how do you introduce the person who is actually known as the father of MEMRISYS. He's actually known as the father of many, many different things, of cellular neural networks, nonlinear circuits, but also the father of four wonderful daughters. And it's really a privilege to welcome not just him, but his family here who are with us today. I was trying to see all the honors that, Leon has actually achieved because of his many, many contributions in the field. And I was astonished to count, and probably have missed some of them, but I counted at least 16 honorary doctorate degrees. I'm not going to go on because we will need the full hour to introduce Leon, but it's really a great privilege to have him with us. And without his work, actually, we wouldn't be able to be here today, talk about MEMRISYS technologies. So, Leon, thank you so much for being here. The floor is yours.
Thank you. I need where's my pointer? Yeah. Everything's, the controls here. Yes. Yeah. And this is right, left. Okay. Okay. Good morning, ladies and gentlemen. Before I go on, I want to show you something. You're going to see this toward the end, at the end of my talk again, but what you're seeing here is something very important. The wafer contains more than 1 trillion MEMRISYS, working MEMRISYS, every one of them. And this is my title in the future. This is the future. As all of you know, Intel was a leader for many years, and it was built upon CMOS technology. But Intel is on its way out with CMOS as the workhorse. It's on its way out. MEMRISYS is going to be the replacement. It's going to be the future workhorse. And it will be for AI revolution and for brain-like computers. So this is part of the stimulation that I hope impart today. So to talk about the future, let's go back first from the beginning, because without the beginning, there is not today. What you're seeing here is Luigi Galvani, and in this important date, January 26, 1781, in his laboratory, with his playing with frog leg, all sort of things, and so on that particular fateful day, 1781, that's an important date for my talk today, Galvani was astonished to find that the frog leg could be induced to contract by using a Leyden jar that's almost completely discharged so as to be undetectable with the most sensitive electroscope. So Galvani posed this fundamental question that we now know the answer. And that is, how could it be that such a tiny electrical force would produce muscle contraction if it were not setting in motion by some internal force? You will now learn today that that internal force comes from the edge of chaos. But about 80 years later, Julius Bernstein, one of the most famous German physiologists, was trying to demonstrate that the spark that led to the frog-leg motion and is a pulse. And so he invented a machine called a rheotome. A rheotome is the name of the machine invented by Bernstein for the sole purpose of showing an actual waveform that led to the contraction of the frog leg. And he was successful, almost anyway. In fact, so successful that he was widely respected. Unfortunately, he became too ambitious, and he claimed that he had explained everything, and he called the Bernstein membrane hypothesis. And in this hypothesis, Bernstein said axons are surrounded by membrane selectively permeable by potassium ions at rest. But during excitation, the membrane permeability changes due to other ions. But he insisted that it was the potassium ion that caused that thing. And that was his hypothesis. And was membrane's wrong hypothesis was taught in physiology for over 50 years. Remember, 50 years. It was incorrect, but it was taught for 50 years. Bernstein's hypothesis, which curiously ignored or discounted one of his own major results, namely the overshoot of action potential, had misled an entire generation of neurophysiologists. It was not until about 1940 that this error was corrected and the overshoot of the action potential became firmly established. And this is the famous result by Haskin and Huxley. And what you saw up there is the action potential recorded by them and published in Nature in 1939. This is the major result that overturned Bernstein's hypothesis. Now, the main result of this result is published by Haskin and Huxley in this famous paper here. And in the first page of this paper, below that, you will see, sorry. This is the first page of the paper, this famous circuit. On the same page, there is what Haskin and Huxley call as sodium resistance, because Haskin and Huxley claim that there are channels from the membrane that secrete potassium ions, and there are channels that secrete, sodium ion and potassium ion, and they were represented by time-varying resistance, time-varying sodium resistance, and time-varying potassium resistance. That was the main result. But there's a serious problem, as you will see shortly on, but they did get the Nobel Prize for this work. Okay, sorry. This is considered the greatest paper ever published in physiology, the paper I just cited. And this paper, let me now briefly say, is based on this giant axon. You see the axon here. They're huge, so huge that you can actually insert an electrode, and that's how they can make measurements. And the giant axon, by the way, is often confused with giant squid. A lot of people thought giant axon is giant squid, but giant squid is huge, about a meter long, and this is a picture of a giant squid. And they're not, giant squid has nothing to do with giant axon. Okay? Now, physiologists have struggled for more than 100 years to invent an electrical circuit motor that could generate an action potential until Haskell and Huxley published the classic circuit that you just saw. And that was the classic circuit that you just saw on top now, emphasized here. And they claim that the membrane is made up of sodium and potassium channel. But nobody ever seen this and can prove that they actually exist that. So the question, are ion channels actually real? Because nobody ever seen it. Until 1964, no one knows whether the potassium and sodium ion channels that are postulated by Hodgkin and Huxley in 1952 Nobel Prize paper actually exist. It turned out that there is a magic bullet proof, which proves that sodium and ion channels are real, that come from Fuku. The sodium channel actually exists, and it comes from Fuku. So what's Fuku? Fugu is a little fish here. You can see that fish in front with the mouth. So this is called a fugu. And this is the side view of the fugu. Or in English, we call it puffer fish. The puffer fish is a very expensive delicacy offered only in high-end gourmet restaurants in Japan. It turned out that fugu is also deadly, because the ovary of fugu contains deadly poison molecules called tetrodotoxin, which plugs the pore of sodium channel. So if you can demonstrate that it stops the action potential, then it proves that it exists. It's also deadly, by the way, because tetrodotoxin is 1,000 times as powerful as cyanide. The Japanese emperor, in fact, and his family are prohibited from eating the supreme Japanese delicacy, fugu. So what blocks, so this fugu is prohibited, and it proves the existence of the sodium ion channel. Now, but what about the potassium channel? What blocks that? It turns out that scorpion toxin blocks the potassium ion channel by binding tightly to a site within the channel pore. McKinnon used the toxin, in fact, to identify the precise stretch of amino acid that form the inside wall and selectivity and fill the channel of potassium ion. So that proved also the potassium channel are real as well. This is the scorpion. So that proves that ion channels exist. But nobody actually really did it and actually show it, except Erwin Neher and his associate. Now, there's a problem, anomaly, by the way. The anomalies that Huskin and Cole have independently measured from squid axon membrane gigantic inductances and DCDI curve that look like rectifying diodes. And these inductances that they actually measure are in almost about a Henry, or 0.8 Henry. That's incredibly large. And they are rectifiers. And I'm holding one, by the way. That's about almost 1 Henry. And the brain can have something like that. So something's not right. Kenneth say that the suggestion of inductive reactance anywhere in the brain was shocking to the point of being unbelievable. But what is good, what is right about Huskin and Huxley is that they have equation that they derive from, based on empirical data, very careful analysis, and produced these 4 fantastic differential equations with 4 state variables. And I want to point out especially the variable here. There is the voltage. There is a voltage on top. There is a variable called N, M, and H. Don't worry about the detail, but there are 4 state variables. And this is part of my talk today, because those are the critical variables that generate the action potential. Huskin had struggled in vain searching for a physical interpretation of squid axon inductance. He failed because he had mistaken the axon for time-varying conductance, when in fact it has a simple explanation. If the potassium and sodium ion channel are identified as memristors. So this is where memristor comes in. It turns out that they are both memristors, and they are not time-varying inductance or time-varying resistances. It turns out that the voltage-gated ion channels are memristors. Let me move on now. So what we now know is that instead of the original Huskin-Huxley model, the mistakes of this sodium conductance is actually a sodium memristor, and the potassium conductance is actually a potassium memristor. That's the major result, and these are the ion channel, sodium ion channel, and potassium ion channel. Now we know neurons are poised near edge of chaos. And this is in a paper that was published some years ago. Although Huskin-Huxley equations have been around for more than 70 years, we still do not understand the complex nonlinear dynamics responsible for action potential. We're going to study in some detail today about some strange complex dynamics today. But let me repeat, synapses now we know are memristors. And these are the synapses now, they are memristors. Now I want to show you several real examples. What you see here is a sea slug, and this is the first slide that Eric Kandel, who had a Nobel Prize, and when he went up to receive the Nobel Prize, the first slide he showed is this slide, wearing a Nobel model. And that was then Eric Kandel receiving the 2000 Nobel Prize. And it turns out that this is a sea slug. And if there is a siphon here which is very sensitive, if you so much touching it with a paintbrush, it would sense danger and retract and generate some signals. And so, for example, Kandel, in his Nobel Prize lecture, showed that the experiment, he made 15 such intrusion, and so 15, he showed only 5. So they're all identical. 5, so he showed only 1, 2, 5, 10, 15. There are 15 identical experiments, each time the same. And what Kandel found is that, and he recorded only 5 of them. The first one is a big response, action potential, and then they're all identical input, yet the next few begin to be diminished and diminished until eventually it was almost insignificant. So I call that a deja vu response of the snare. Snare's name is Aplysia. And that was the main presentation in Eric Kandel's Nobel lecture. And we can now reproduce exactly the same thing with a memristor, or one memristor. We have now 15 input identical, and we pick the same 5. This is the Eric Kandel's 5 selection, 1, 2, 5, 10, 15. We picked also 1, 2, 5, 15. And you can see that it also diminished until to be insignificant. So it shows that the memristor, in fact, is the one that Eric Kandel was passionate about. And so that was the first example to show that the memristor is the main role, play main role in that Nobel Prize. Next is another Nobel Prize. In 1970, Josephson received a Nobel Prize for inventing another circuit that emulated superconductivity. And his circuit consists of capacitor, inductor, and a symbol here that turned out to be an inductor, well known. And they all have equations. That's how he got the Nobel Prize. But Josephson also added something, which he apologized that he didn't know what it is. But he said it's very small, so you can ignore it. But he gave the equation. He said, this is the equation from quantum mechanical quasi-particle interference theory. He can produce that equation. He said, didn't know what it is, but he said, don't worry, it's very insignificant. So his Nobel Prize is okay. Today we now know that this is a memristor. So this is the second Nobel Prize that's actually based on a memristor. Not exactly, but it was where memristor plays a role. That was Josephson. So we now know that the fourth critical element is a memristor. Then come earlier, fast forward, 1904, Nobel Prize in Physiology, Medicine, given to Pavlov. So Pavlov experiment is, he had a dog. By the way, my daughter down here, is Katrin, is helping me here today, and his dog's name is Frodo. So this is Frodo. Frodo was shown ring a bell, and he was indifferent. Frodo doesn't care about the musical chimes. And when Frodo was shown a piece of meat, he salivates. But Pavlov had the good sense to do the next thing. Pavlov will show both of them, the meat and the bell, to Frodo. And then few minutes later on, it was shown only the bell on the lower left is shown only, and Frodo salivates. So he was associating the beef with the sound of the bell. So that's called associative memory. Associative memory and learning is defined as the ability to learn and remember the relationship between unrelated experience or events. In fact, in 350 BC, Aristotle had already suggested that learning involves association of ideas. A few years ago, Professor Miao and his group, and he put my name, by the way, downstairs, published a paper in Advanced Materials and showed that this circuit with a memristor on top and 2 resistors below and 2 voltage sources on the left voltage source emulates the bell. And the second voltage source emulates the meat, and then the output is out here. You can see in the lower right part. And you will see now the result. On top is the bell, or the signal of the bell. The second one is the foot. So the third row is the measurement. So you can see in the first 3 signals, the foot is there, so there's a response. And then further down, there's not only the bell, so there's no signal, output signal, because Frodo doesn't care about the sound. Then the next one when both the bell and the foot are aligned, and then there's an output as expected, and then after that, there is no more foot, only the bell sound on top, and there's an output below that emulates that circuit. So that shows that, and this is published in Advanced Material, as I said, in 2019. It shows that the memristor plays a critical role there. And the next experiment is also published Advanced Material in 2014. What you see is a catapult, and Professor Chang-Fu Wu, actually from Berkeley, won a prize for this paper, by the way, and he was invited to the White House for this achievement, and President Obama was greeting him. And what this consists of is, on the left side, you have two identical vanadium dioxide coils, and it's connected in the middle with a little kind of a basket so you can hold a piece of object there. And that, in the end of this, in the end, these two terminals, you can make measurement, and it turned out it's a memristor. So that proves that's a memristor. And the next slide shows that when you put in a micro object, say a little tiny piece of object there, that block object, the thing, you see the spring, the spring actually flip, okay? Yeah. It turns out that what you're seeing here is a very powerful property of this particular device. And to compare that with the performance of a turbofan of 777, the power density of a turbo, of the plane 777 is 9 kilowatt per kilogram, and the rotation speed is 10,000 RPM. The performance of the micro catapult that you just saw is 39 kilowatt per kilogram, and a rotation speed of 200,000 RPM. That's incredibly, that tiny thing. And so this is just as powerful as that, and it just shows that this actually memristor is tremendously powerful energy converter. Now I want to show you a glimpse at the edge of chaos. I want to be sure that I'm on time. Yeah. Well, a glimpse of edge of chaos. Instead, it will take me half an hour to explain what edge of chaos is, but today I'm just going to explain to you by telling you that we have a test of when you have an edge of chaos. I call this the Nyquist test for edge of chaos. And that's the following. If you give a two-terminal device, and you want to find out whether it has an edge of chaos domain or not, so as I say, a two-terminal device or one port biased at a stable DC operating point on an edge of chaos domain, if it has an edge of chaos, if and only if the Nyquist plot, the Nyquist plot is defined as just a plot of the imaginary versus the real part of the admittance or the impedance, and so everybody knows that intersects the imaginary axis or is located on the left half plane, real part of the admittance on the left half plane. So this is the Nyquist test, and let's take that as a definition of edge of chaos because you can measure that. So testing edge of chaos involves only linear algebra, and here's an example of edge of chaos. So in that, on top here is the real part of the admittance of the candidate to be tested for edge of chaos, and this is the imaginary part. And when you plot the imaginary part versus the real part, there's a name for that. It's called the Nyquist plot. Most electrical engineer knows that. And this is, therefore, the Nyquist plot of that example. And if this intersects the vertical axis, the imaginary axis, or if it is on the left half plane, you have an edge of chaos. So Huskin-Huxley model, this is Huskin-Huxley model, by the way, okay? And the Huskin-Huxley model is on edge of chaos if its Nyquist plot intersects the imaginary axis, and it does. So that's what edge of chaos means. And it can be tested, as I said, and when you plot that in this frequency versus either on the right side is either the voltage or the current, you can see that only the tiny edge, satisfy the edge of chaos property. A very tiny region, even though there's a huge candidate. And so the range of edge of chaos, in fact, is very small. The current, if you drive with a current, the range is between 1.94 microampere. I mean, the external current of the Huskin-Huxley model should be only within that range. And that means that only 1.94 microampere, or in terms of voltage, it should be within that range, in the edge of chaos, and only 0.77. So that's amazing that you and I are all alive because we have this ability. And so this is the window for life to be possible. You can have 2 microampere or 1 millivolt, and to be on the edge of chaos. Now, let me just fast forward to tell you that the edge of chaos is a special case of a general principle that I developed. It's called the local activity principle. It's very complicated. I'm not going to have time to talk about it today, but this is the fundamental result. It's a foundation for science, not only circuit theory, but for science. Edge of chaos is a special case of the local activity principle. And to prove that the local activity principle is very, very complicated. It requires all of these mathematical theorems, and people would ask, how come these are all deep mathematical results? How come the mathematicians didn't discover this? And the reason is you need one more item. It's called Telegen's theorem, which is a circuit theory result, which mathematicians didn't know. That's why nobody knew about this. And I developed this theorem. I discovered it by putting all this together. This is the fundamental result. Okay? So edge of chaos is the pearl of amidst the locally active domain. And the physical meaning is one can use locally active cell to amplify small signal at the expense of an external power supply. Fundamental new result of chaos theory said that a stable equilibrium state can be destabilized by coupling it to a positive environment if and only if the equilibrium point is on the edge of chaos. Now I'm going to fast forward now to tell you that local activity is in fact the origin of complexity, and action potential is impossible without edge of chaos, and the neurons are poised near the edge of chaos. Now, let me move forward. There are now several papers published within recent years. In 2023, Professor Joshua Young and Zhang Fei and others have published important papers, 1,000 of conductance levels, monolithically integrated in CMOS. This is a major result of achievement. And then next year, 24, by Professor Joshua Young, Zhang Fei again, and colleagues, have a major paper that show you can program membristol array to solve major problems. In particular, you can solve Navier-Stokes equation. You can see the Navier-Stokes equation is simulated on the left, and it's solved by the array of membristols on the right, and they are almost identical. Now, there is the latest one is just published two months ago by Professor Chang Fei Xia, a major paper, showed how you can apply this for major applications in communication systems. So, and finally, there's a paper published by Mario Lanza and colleagues in 2025, the growing membristol industry. But I'm going to now fast forward to look at the neuron. This is a typical neuron. There are more than 100 billion neurons in the human brain, in your brain and my brain. So how many is 100 billion? Well, it turns out that every star that's bright enough for the naked eye to see belongs to the Milky Way galaxy. And it's over 10 to 11 stars. So our brain has just about as many as the Milky Way stars. That's how many it is. And now we are going to probe a particular neuron. We're going to inject on the left side input. So we're going to inject it's not working very well. Yeah. Anyway, on the left, you can see the current. We injected the current, and then we're measuring the response. And this is the diagram showing the graph between the voltage of the Hawking-Huxley motor and the input current. It was cut off in the bottom. And the edge of chaos domain is just somewhere there. And I want to show you now that there is a tiny read domain here that is the major reason for my talk today. It turned out that, for example, if you apply an input current on the left side, Ix, wait a minute. Yeah. If you apply a current, if you apply a current here, which you can read, okay, but let me just tell you that that current, has 13 decimal digits, and in the end of that is number 1, is 1. Now I'm going to just change that 1 to 2. First of all, with that input, any excitation leads to a steady state. That means it's DC, no output. But just as soon as you exceed in the 14th decimal digit to 2, it suddenly becomes action potentials. It's that sensitive in our brain. And the next one, you move from 2 to 3. When you go to 3, it's back to nothing, just the steady state. And the next one, 4, is again trend of action potential. It is so sensitive, and this is quite amazing, but this is repeatable, okay? Now, it turns out that if you plot this result, and the abscissa, remember, they are 4-state variable. I can only show you one M and the other one is the other state of the voltage. There are four, I can show you only two. I'll show you the voltage of the Husky motor, and this one is one of the for the M. And this is for a particular input, you see the response. When you see the red, when you see blue, that means the response is DC, and just constant, nothing. And then when you see red, it means you got a spike trend. So that would be the more common situation. But if you change that slightly, suddenly it began to mix up. And if I keep you see, for example, this is a plot of the voltage, sorry. What are you seeing here? This is the voltage at the initial condition. This is H, that's one of the four-state variables. You can see now that all the blues and the red are now all mixed up together. You know, so it's now very, very noisy. I actually showed that some years ago, but I don't know where it came from, and thought that may be just some experimental error. But turns out this is robust. Okay, and see how noisy it is. This is the plot of the voltage, initial voltage, with initial N, and it's so noisy. And I showed that for some years ago. I don't know why, how it happened. And today I'm going to show you that we now know the answer. So to know that, I have to introduce a language here. First, there is such a thing in mathematics. This is now going to be mathematics. There's a such thing called a Cantor set. Cantor is a person, mathematician. I'll show you a picture shortly. Shows you if you have a line, say one centimeter or 1 meter long, if you make several operations, first you divide into three. So 1/3, 2/3. And then the next time you repeat, you cut away the middle third, and you repeat. And you keep doing that. Whatever that remains, when you do this continuously to infinity, that set is called a Cantor set. Now that's going to be very relevant because this is exactly what's happening to the strange noise pattern that I didn't know how to explain. We now know how to explain. So this is the Cantor set in color. And because we have coordinate, we can calculate, okay? So you can calculate all this number and actually find out what is the common in the end intersection. It turned out that, so what is the length? Let's call the intersection of all of them C, capital C. What is C? Well, C1, C2, C3, etc. are all calculated because we have the formula. But finally, it turned out that the total length of the Cantor, it's called the Cantor dust, by the way, because in the end it becomes so tiny it's like dust. The total length of the Cantor dust is 0. Okay, and that's George Cantor. And C, it's called the Cantor set, is uncountable. It turns out that what you saw in this inexplicable noise is in fact a Cantor set. So it turned out the Husky circuit motor exhibits a fractal basin of attraction. What you saw all this is called a fractal basin of attraction. And to understand that, we need to understand the truly fundamental math result is by Stephen Smale. And in just a few months ago, I was invited to give one of a lecture in the 95th birthday of Stephen Smale's birthday. celebrating his major accomplishment. Stephen Smale, this is the signature picture of that. Stephen Smale, awarded the 1966 Fields Medalist. Awarded, this is, to many people, this is more prestigious than the Nobel Prize. Why? Because Fields Medalist is awarded only every 4 years, and only to a mathematician under age 40. That's remarkable. And Stephen Smale is that, and for this result, in fact, that I'm going to tell you now, this is called the Smale horseshoe. What is the Smale horseshoe? Imagine a square there. Look at the square. Well, I can't point that well enough, but look at the top left. That's a square of points. In mathematics, just a point, fair point. But today, think of this as dough. You make a. I brought yourself just to make it more dramatic. If you want to make, if you're a baker and you want to make a croissant, we're going to make a croissant, okay? And you start by a piece of dough, flatten it up, and imagine that you have, say, 2 spots of ink on that croissant, and you keep rolling to get a croissant, and you want to find out what happened. Where do those 2 points go? Nobody can answer that, of course, until Steve Smale came along and said, he can do it mathematically. He can track them and tell you exactly where are those 2 points going. A remarkable result. Less than 40 years old, he was able to do that, and it was amazing. And there was the 95th birthday celebration. Okay, so the first thing you do is you flatten the dough from the left, upper left, to the upper right. It becomes, of course, skinny. And then you bend it, go down here, you fold it. You fold it, you see that, a horseshoe. And then you chop off the end. You chop off the end, you now have 2 horizontal filaments or points, like on the left, and then you repeat the process. Flatten them, and then, so you now have 2, from 1 to 2, and then do the same thing, bend it, and keep doing that. And if you put 2 points in there, you ask, where does it 2 point go in the end? Well, of course, this is impossible answer until Smale got his Nobel, his Fields Medal, because he can tell you exactly where those 2 points are going to end up. A remarkable achievement. So this is the croissant analogy, and this is the folding operation, and this is part of this operation of the Smale thing, and this is part of the very complicated structure, okay? And it turned out that in the year 2002, there's a group of professors, Guggenheimer and Oliver from Cornell University, actually published a paper that's not well known, but it's very significant for today's talk, because this note demonstrates previously unobserved dynamics in the Husky-Huxley model, namely the existence of chaotic solution in the model with its original parameters. The solutions are found by displaying rectangles in cross-section whose images under the return map produce a Smale horseshoe. The chaotic solutions are highly unstable. They're significant in the sense that they lie in the Bayesian boundary. So this is the fundamental result that connect the two. And it turns out that this is now from the Husky-Huxley model, and it shows now that the strange attractor is the Cantor space, and Smale's theorem says the cross-section of strange attractors are Cantor space, and we can now state Husky-Huxley equation has a Cantor set, and such that it contains countable set of periodic orbits of arbitrary long period. It contains an uncountable set of bounded, no periodic motions. It contains a dense set, which is a bit too mathematical to explain today. And so the visions of memristors on edge of chaos. Let me now move on, say that edge computing is a distributed information technology architecture in which data are processed in proximity to the sources. For example, sensors or Internet of Things devices that generate them. In traditional computing approach, data are preliminarily sent to a remote center before elaboration. This unavoidably slows down the extraction of information as transfers of procedure is susceptible to bandwidth limitation, latency, and potential disruption of the Internet. Another major issue is the huge amount of associated energy consumption. The energy consumption for sending data to a data center is more than 10 times that of preserving locally on the edge using MEMRISYS system, because sending data involves converting analog data to digital, storing them, and transferring them over long distance. A distributed signals processing system is of vital necessity for time-efficient energy solution demanding computational challenges involving frequently big data era that we are currently living on. So let me now move on to tell you that in the past 3 years, there has been an increased emphasis on solving practical design challenges for implementing neural MEMRISYS solutions for energy-efficient computing on edge. The complexity problem at edge keeps on increasing in problems such as autonomous driving, surveillance, tracking, multiple object real-time tracking of humans, all of which demand increased computational density, at the same time need to meet low energy requirement. The most important advancement now is compute in memory, CIM. There's a new company called TetraMem. This is the origin of that picture that I just showed you earlier on. It's early energy serving estimate for data center scale workloads shows CIM approach can reduce power consumption by orders of magnitude, such that vector matrix multiplications, energy serving MEMRISYS-based CIM using MEMRISYS-based in-memory compute. So this is the company, new company called TetraMem that produced that chip that I showed you earlier. And that is the TetraMem, and in fact, I believe I have it right here. This is so precious. This is an actual working chip. Just to show you, this is one of the billions. There are since a trillion memory stored in there. This is one of these billions of chips in there. These are all operational, and just to show you that this is real, produced by this company. And this is the company that I'm talking about. It's called TetraMem on all the. So this is going to be the future Intel, in my opinion. I want to thank Dr. Glenn Gay, Joshua Young, and Xiang Fei from TetraMem, and for the leadership in this MEMRISYS-based type of computer. And I want to end toward the end to show you that Geoffrey Hinton, who was the great-grandson of George Bull on the left, he just received a Nobel Prize, in fact, not even a year yet. So when he gave a talk, he didn't know he's going to get a Nobel Prize yet. But he has a strong prediction that I copied. He said about a new type of computer from Geoffrey Hinton, who didn't know he's going to get a Nobel Prize yet last year. He said, we are going to do what I call mortal computation, where knowledge that the system has learned and the hardware are inseparable. If we do that, we can use very low power analog computation. You can have trillion-way parallelism using things like memristors. I was surprised that he knew about memristor. In fact, he was predicting, in fact, that's the only device that can make this happen. And a few months later, he received the Nobel Prize. Now, I'm going to move forward toward, it turned out that there's a connection here. Marcel Proust published a fantastic volume of literature here. This is a 2-volume book by him. The title is Remembrance of Things Past by Marcel Proust. So the French name is on top. It is 3,200 pages in 7 volumes with more than 2,000 literary characters. One of the sentences in Marcel Proust's book is about 2,500 words long, just to show how remarkable this author is. And Somerset Maugham said that this is the greatest fiction to date. So what's the big deal about that? Well, Remembrance of Things Past is just the poetic equivalent of associated memory. Proust's childhood recollection of associated memory between Madeleine and the tea predates that of Pavlov's experiment. So just to recall Proust's childhood, he would go back every weekend to his grandma, and he would be sipping tea with Madeleine. So tea and Madeleine. He's associating tea with Madeleine. And the 3,200-page novel is sprinkled with numerous episodes of associated memory. So now listen carefully and try to recall Candel's and the medal in the Aprecia. They're connected. Remember that after a few times, the Aprecia got tired and they ignore it, okay? Well, Candel essentially is having the same experience. He said, I drank a second mouthful. First, he had a cup of tea with Madeleine, he liked it. The second time, he said, in which I find nothing more than just the first. And the third gives me even less than second. And it's a time to stop. So he's getting less and less. It's deja vu. He's doing exactly the same phenomena way back. Proust had just discovered deja vu response in his own language. And I want to end up with a sonnet 30 from Shakespeare, because this is the sonnet. Shakespeare, you all know what a sonnet is. You got 14 lines. So the first 2 lines I'm going to read to you. When to the season of sweet silent thought, I simmer remember of things past. Remember of things past. So that is from Shakespeare, okay? And now I have a 4-word definition of a memristor. If you want a simple definition of memristor, it's simply remember of things past. 4 words. That's exactly what a memristor is. Thank you for your, thank you. Have I gone over time? I know.
We are exactly.
Yeah.
Thank you so much, Professor Chua. Each time I see Professor Chua presenting is equally fascinating, and it's been really, really great to be able to see from the man himself of innovations that came up in so many fundamental different areas that he developed, like more than 55 years ago, coming to fruition. It's been really enlightening to see also the most recent work on the Age of Chaos and using the Hodgkin-Huxley work as the prototypical example to bring this all together.